Now we are down to the third topic for prelims, which would be the proteins. And in this PowerPoint presentation, we are going to talk about the amino acids and their molecular formula and structure. And I know that most of you already knew that amino acids are basically building blocks of proteins. When we say building blocks, they are the small molecules that basically make up a specific macromolecular structure or compound. So without these building blocks, your macromolecular compounds such as proteins won't be able to be formed. So yeah, again, we are going to talk about the molecular formula and structure of your amino acids and also the classifications of amino acids. We have the polar, non-polar types of amino acids and the neutral ones, of course. And we also have the peptide bonds, which are the bonds that are formed between two amino acids in order to form a bigger structure, and that specific what formation will just go on until such time that we will be able to have a one big molecule such as your protein. Now, before we discuss further about proteins, let's first have a review on these basic terminologies that I guess you've already encountered these ones during your basic chem. So I've uploaded a separate video regarding this review, so kindly access that video, and for sure the content of that specific video will appear in your prelim examination. And I need you to take note of the definition of these terminologies because we will be encountering these terms as we go along with our discussion discussion on proteins. Also, in the other video, I will be discussing about the L form and the D form. The L will basically stand for the term levorotatory, and the D stands for dextrorotatory. So kindly access that video so that you will be somehow enlightened or be reminded of the definition of these terms. And so we will be able to avoid that specific confusion as we go along with our discussion in proteins or discussion on proteins. So let's have our formal discussion on protein. And I guess you've already have your organic chem before, so you're not unfamiliar with the term protein. This is a naturally occurring unbranched polymer in which the monomer units are amino acids. So monomer units, that's just the same thing as, calling it as basic units, right? So basically, a specific protein is composed of amino acids, which are what we call basic units. A protein molecule could have the carbon atom, hydrogen, oxygen, nitrogen, and sulfur atoms in its molecular structure. So Johns, remember that one.
Now, your amino acid usually contains a carboxyl group, which you can write in this way: COOH. This is the shorthand version. Or you can write it in its expanded form, which is C for carbon atom, being attached to an oxygen using double bonds, and the same carbon atom is attached to a hydroxyl group or OH. So these are the two ways on how to write a carboxyl group. Now, the carboxyl group is just one of the functional groups that you can find in the molecular structure of your amino acid. The other functional group that you can find in the structure of your amino acid is your amino group, which you can write in this way: NH2, sorry, this is NH2, which means it has a specific nitrogen atom, and that specific nitrogen atom is bonded to two hydrogen atoms. So this is the shorthand version of writing the amino group. You can also write the amino group in its expanded form. So you can just write the nitrogen atom and just attach the nitrogen atom to one hydrogen atom, and the same nitrogen atom is attached to another hydrogen atom. So you have one nitrogen atom attached to two hydrogen atoms using single bond. So these are the two ways on how to write the amino group. Your amino acid also has a side chain which you can just denote as R in its molecular structure. A side chain can be any functional group. Could it be or it could be an aliphatic group, an alkene, alkane, alkyne. It depends. It depends on the type of amino acid that is being introduced. But anyway, if you if we would complete the structure of a specific amino acid, we will be able to write that one in this way. So you have a central carbon atom, which we've already talked about that one in the previous video, a central carbon atom being attached to one hydrogen atom and to a specific side chain. Again, the side chain will vary. It could be a side chain that is aliphatic, that is alkane, alkene, alkyne. Um, it all depends really on the type of amino acid. And of course, to the left of the central carbon atom, you have the NH2 or your amino group. And to the right of your central carbon atom, you have there the C double bond OH or your carboxyl group. So this is how a specific amino acid would look like. I mean, how a molecular structure of your amino acid would look like. And all amino acids will vary lang din sa ilang side chain. Again, this one will vary depending on the amino acid. So basically, the R chain is the distinguishing characteristic. Again, this is the distinguishing characteristic among amino acids. Now, amino acids are usually on the L conformation, which means they are levo-rotatory. Rotatory. And I've already explained this one in the previous video, right? Regarding levorotatory and dextrorotatory molecules. At physiologic pH, when we say physiologic pH, it could mean the normal blood pH, which could range from 7.35 to 7.45. So at physiologic pH, amino acids would usually carry a positive charge on their amino groups. So guys, ano yung itsura ya? NH3+. And amino acids will also carry a negative charge on their carboxyl group. So, ano yung itsura ya? C double bond O with negative charge. I will explain in the succeeding slides how come your amino acids would look like this once they are exposed to physiologic pH. But for the meantime, kindly memorize this specific molecular structure or molecular formula of your amino acids when they are in physiologic pH. Now, the side chains, or what we usually denote as R, of the amino acids contain different chemical groups, just like what I've mentioned in the previous slide. That is the distinguishing characteristic of your amino acids because sa side chain lang sila galain-lain sa chemical group na gina-carry. Again, the chemical group that they could carry would be alkene, alkane, alkynes. They could also contain benzenes and etc. Some side chains can also carry a charge. This is where this is basically where we will be able to differentiate your amino acids into polar amino acids or non-polar amino acids. Or this is where we will be able to distinguish amino acids as acidic or basic amino acids. Sige lang, we will discuss about the different classification of amino acids in the succeeding slides. Peptide bonds link adjacent amino acid residues in a protein chain. So guys, we have one amino acid, let's have AA lang nanay. One amino acid and another amino acid. They can be bonded together with the use of peptide bonds. Peptide bonds are also known as amide bonds. Again, peptide bonds are also called as amide bonds. So basically, these are the bonds that connect amino acids to one another. So if we have a long chain of amino acids that are being attached by peptide bonds, we will be able to form a long chain of amino acid that could later on fold. They will fold to form a complete and functional protein, right? So without amino acids, without amide bonds or peptide bonds, there will be no protein. Now let's have a short review on the functional groups, most specifically the functional groups that are a part of the amino acid structure. Let's have for the first one, the carboxyl group. This is an organic functional group consisting of a carbon atom which is double bonded to an oxygen atom and single bonded to a hydroxyl group. I've already mentioned this one in the previous slides. So the carboxyl group is commonly written as C double bond O, OH in a shorthand version, or we can just, simplify that one as COOH. So it's just understandable that one of the oxygens here, especially the one adjacent to your carbon atom, is double bonded to your carbon atom. So it's fine if you write your carboxyl group in this way, or if you want to write the carboxyl group in this way, or you can just write it in its expanded form. No problem at all. So another functional group that we can find in the structure of your amino acid is your amino group, which is consists of your nitrogen atom that can be attached by single bonds to a hydrogen atom or two hydrogen atoms. It can also be attached to an alkyl group or aryl group, or the nitrogen atom can be attached to a combination of these three groups. So basically you have NH2, or if we write it in its expanded form, it will look like this. Or your your nitrogen atom can be attached to a hydrogen atom and another one to an alkyl group. For example, methyl CH3. Or your nitrogen atom can be attached to a hydrogen atom, and the other part of it is attached to a specific aryl group, or a group that is basically derived from an aromatic ring such as your benzene. So for example, this one, yeah, this is just some of the examples. But anyway, this is how a specific amino group would look like. It can contain a nitrogen atom that is attached to hydrogen atoms, or it can be attached to alkyl groups and aryl groups, or a combination of these three. Any organic compound that contains an amino group in its structure is known as an amine. So basically, your amino acid is an amine compound because it contains a specific amino group in its molecular structure. That's why it is known as your amino acid.
Amino means it contains an amino group in its structure, and the acid is usually to denote that it contains a carboxyl group. Or, yeah, anything that contains carboxyl group in its structure can be known as a carboxylic acid. So yeah, that's why amino acids are known as such, are called as such, because they have an amino group in their structure and the carboxyl group in their structure. So again, your amino group can be written in this way, NH2. Now, the alpha carbon atom is the first carbon atom that attaches to a functional group. By extension, the second carbon is the beta carbon. So for example, we have here a functional group, which is your carboxyl group. Again, your carboxyl group. And the first carbon atom that is attached to your carboxyl group is known as the alpha carbon atom. Next, adjacent to your alpha carbon atom is your beta carbon atom. This is just we just revisited alpha carbon now because one of the slides wherein we will be talking about the classification of amino acids, we will be able to encounter a specific amino acid, and one of the contents of of our discussion will be about the will have something to do with the alpha and beta carbon atoms. So anyway, don't stress out yourselves about the alpha carbon atoms because this is just a review. But anyway, you just have to remember that your alpha carbon atom is the first carbon atom that is attached to a specific functional group, and that the carbon atom next to your alpha carbon is your beta carbon atom. In nature, the vast majority of amino acids take the L configuration as opposed to the D configuration. That means mostly they are left-handed more than the right-handed form. The L and D configurations are enantiomers, which means they are mirror images to one another. Mirror images, which means they may have the same chemical structure and order to their molecules, right? But the way the molecules or the atoms are arranged in space are opposite or opposing. I've already discussed this one in the previous video, so if you're still confused about the L and D form, the laboratory and dextrorotatory terminologies, kindly revisit the video that I've posted before this specific discussion. Molecules with enantiomers polarize light that is shown through it, and they can be assigned an L or D based on which the light bends when shown through a solution. Most amino acids naturally only occur in the L conformation, which makes them enantiomerically pure. So take note, most amino acids are in their L form. Interestingly enough, most medications are only active in one of the two conformations, and the enantiomer actually causes the side effects associated with that drug. So, guys, when we speak about, drugs or medication, please always remember that a specific active compound of the drug can be in its L and D form, right? One of the enantiomers, or one of the forms of the active compound, can provide the desired pharmacological effect. And the other enantiomer, or the other form of the drug or medication, can cause the side effects.
of the drug. So for example, you have colds, ginasipon ka, you have colds. Now, of course, you have to take medicine. Now, that specific medicine has the L and D form. Let's say the L form of that specific medicine can alleviate the symptoms, which means pahinayon yung rate of mucus production, and then madula ang blockage sinuses, so on and so forth. Now, let's say the other enantiomer, which is the D form, can cause side effect. Let's say the side effect is drowsiness, right? So in this specific example, you can have one medicine that may have an active compound in its two configuration or two forms, the L and D. One of the forms or one of the enantiomers could be the one that could provide the pharmacological effect, the desired pharmacological effect, and the other enantiomer or not another form can provide the side effect of that specific drug. However, it isn't cost-effective to isolate the active enantiomer, and the side effects generally aren't that bad enough to warrant a need for it, except for the drug known as thalidomide, because this drug comes with side effects that could basically harm the babies. So thalidomide is basically provided to pregnant women before. Thalidomide is a drug that is given to pregnant women before to alleviate the symptoms, signs and symptoms of pregnancy, such as nausea and vomiting. So I kind of forgot the year when was thalidomide, was mass produced. But basically, the thalidomide drug was given to alleviate nausea, and vomiting sa pregnant women. But that time, when this drug first came out, no one knew the side effects of the thalidomide. So more pregnant women were taking thalidomide as prescribed by their physician. Later on, as years passed by, there were a lot of cases of defects um, birth defects with mothers nga nag-take ng thalidomide. And that's the time when countries that were using thalidomide discovered that this specific drug can basically cause birth defects. So there were a lot of stillborns, a lot of kids that were born with, defects, kids that don't have limbs, kids that have disfigured body parts, so on and so forth. So that is again when thalidomide was discovered to be having side effects to babies. So as you can see, thalidomide has a pharmacological effect. That is, it can alleviate or it can reduce nausea and vomiting in pregnant women. But the side effect of thalidomide is causing birth defects naman to babies. However, amino acids are naturally isolated in their conformation, so they are sold as L-amino acid. As we've mentioned, amino acids are usually in their L form, so there's no need for the pharmacological companies to separate the L form from the D form of amino acids, because again, most of the amino acids already come in their L forms, which means this is already the active form of amino acids which can provide the desired pharmacological effect. Now, about 20 amino acids, which we call as standard amino acids, which are used for the synthesis of proteins by mRNA-directed process that occurs in ribosomes. So this specific mRNA-directed process is known as translation, right? Translation, in which the codes in the mRNA are being translated into amino acids. And so these translated amino acids are attached to one another to form your proteins. Anyway, we will leave the translation process to Sir Jericho Carmona, who is your cytogenetics teacher. He will discuss translation together with the transcription and replication process to you. But anyway, please do remember that we have standard amino acids, which are a total of 20. And these are the 20 amino acids that are being combined to one another to form proteins. Other amino acids exist for which there is no genetic code. There may be amino acids, right? Right. Um, there may be a couple of amino acids that exist. However, there are no corresponding codes that will basically code for those specific amino acids. So as of now, as of this moment, only 20 amino acids are known as um, the amino acids that have, genetic codes, which can be decoded during the translation process. Now it's time to talk about the structure of your amino acids. I guess I've already provided you the preview on this one, right? Your amino acids contain the carboxyl group, the amino group, and the side chain or R group. These groups are all attached to the alpha carbon atom of your amino acids. Again, just to refresh your minds, your carbon atom, alpha carbon atom, is being bonded to one hydrogen atom, to an R group or side chain. To the right of it, we have the carboxyl group, and to the left of it, we have the amino group. And take note, we have carboxyl group, which is in which carries positive charge, and the amino group, which carries a negative charge. Take note, don't be confused of this one. Remember in the previous slides, I've mentioned that at physiologic pH 7.35 to 7.45, the carboxyl group will always carry a negative charge, and the amino group will carry a positive charge. Please don't be confused of this one. Nga si carboxyl group, this sa time niya ini may positive charge siya. Na si amino group may negative charge siya. Because guys, this is the molecular structure. This is the molecular structure of amino acids. Um, before exposing to pH. Right. We're just writing the the actual lang yung molecular structure of your amino acids. We're not yet talking about the structure of amino acids in a specific pH. But once we talk about the structure of amino acid that is exposed to physiologic pH, amo na ning itsura ya. Your carboxyl group will now carry a negative charge, whereas the amino group will carry the positive charge. So I will explain in in the succeeding slides, how come nga from this specific structure, mangin amoni ang magwa, mangin suli. From positive carboxyl group, nangin negative siya. From negative amino group, nangin positive siya. So we will discuss that one. Don't worry. Guys, this is the amino acid structure in physiologic pH. Again, this is the amino acid structure in physiologic pH. Notice that the carboxyl group is carrying a negative charge and your amino group is carrying a positive charge. Now, paano naging amoni ang structure ni amino acid? Let me show you how the amino acid was able to have charged, functional groups. To show you the changes, let's first have the original structure of your amino acid. Ano ganing original structure of your amino acid? You have one alpha carbon atom that is attached to the hydrogen atom, and your alpha carbon atom is attached to the side chain denoted by R. Next, your alpha carbon atom is attached to a specific carboxyl group, which is written as C double bond O OH. Again, guys, we are talking about the original structure of your amino acid. Wala na naitalabot sa pH. Next, your alpha carbon atom is attached to an amino group. Amino group gani NH2, which means may duha lang ka hydrogen atoms that are attached to one nitrogen atom. Now, this is the original form of your amino acid. Next, let me show you how the specific structure would change once your amino acid will be exposed to physiologic pH 7.35 to 7.45. Now again, this is the original structure of your amino acid without, you know, um, without being exposed to pH. Now, let's say your amino acid is in physiologic pH na, which means we expose your amino acid to physiologic pH 7.35 to 7.45. Now, what will happen? Guys, the normal behavior of your carboxyl group in physiologic pH is it will let go, again, it will let go, it will let go one hydrogen atom. I-let go yun na guys, si hydrogen atom. So the hydrogen atom will be floating around in the solution. So makakas si hydrogen atom. Now, pagkakas ni hydrogen atom, the carboxyl group will now carry a negative charge. Why? Because your hydrogen atom is a positively charged molecule. Once it is removed from being attached to an oxygen, the oxygen now will carry that specific negative charge. Kaya hindi mo oxygen, di ba, is a negative charge atom? Right. So, since nadula ang pagka-positive ni carboxyl group, the negative charge of your oxygen atom will come out. So, that's why narata nga kinakerry ng negative charge sa carboxyl group. Now, what will happen to the hydrogen atom that was, let go by the carboxyl group? So, the hydrogen atom will go to your amino group. It will be attached to your amino group. From NH2, it will become NH3 plus. Right. It will now carry a positive charge here because your hydrogen atom again is a positively charged molecule. May nagsubra ka nga positivity diri. So that's why mag-carry maging sa positive charge ang imo nga amino group. So remember that in physiologic pH, again, your carboxyl group's normal behavior is to let go one hydrogen atom. It will let go one hydrogen atom. And in physiologic pH, the normal behavior of your amino groups is to accept a hydrogen atom. Accept, let go. Now let's talk about the acid-base properties of your amino acids. So this is where you will see another changes in the amino acid structure once your amino acids are exposed to different pH. Let's say the amino acid is exposed to acidic solution or acidic environment, or that your amino acid is exposed to a basic environment or basic solution. In pure form, the amino acids appear as white crystalline solids with relatively high decomposition points. Amino acids are not that very soluble in water, and they are charged species because of their amino group and their carboxyl group in their molecular structure. That's why they are known as charged species. They will always carry, charges in their molecular structure depending on the pH that they are exposed to. Again, for the nth time, this is the amino acid structure, the default one, which means we don't really need to consider yet at this moment the physiologic pH and any other changes in the pH where the amino acid is being exposed to. This is the default structure. Still, we have the alpha carbon atom, the side chain, the hydrogen atom, the amino group, and the carboxyl group. Miss, okay lang nga ang our chain nara sa babaw, ang hydrogen nara sa dalong? Yes, because we know, kindly remember that your molecules tend to um, what flip. Your molecules can flip, right, horizontally or vertically, which means pwede siya mag-change ang position sa imo nga atoms in space. So pwede nga itsura ya would be this one if mag-flip ta what horizontally, or if we flip the molecule, if we flip the molecule vertically, amo ni itsura ya. We have this COOH here and the NH2. It doesn't matter as long as um, your carboxyl group can be located either in the left or right of your alpha carbon. The amino group is located either the left or right of alpha carbon. And your R chain and your H are always either on top or bottom of your alpha carbon atom. That's fine. In neutral solution, let's say physiologic pH, for example. In neutral solution, um, or kung sa body manggid in physiologic pH, the carboxyl group always loses the proton or your H plus. Right? I've already mentioned this one. Your carboxyl group's normal behavior is to let go a proton or a hydrogen atom. So, let go yung H plus. So, if let go yung H plus, from C double bond OH, mangin C double bond O, O negative na ang iya nga itsura. Now, the proton will be accepted naman by the amino group. Why? Because the normal behavior of your amino group is to accept proton. From NH2, for example, mangin NH3 na lang sa with a positive charge na gina-carry. Please do take note, these are the normal behaviors of your carboxyl group and amino group in neutral solution or physiologic pH. The carboxyl group will lose proton, the amino group will accept proton. What is a proton? That's your H plus. Now, probably most of you still remember what a Zwitter ion is. So, Zwitter ion is basically a specific molecule, a molecule that contains both the positive and negative charge in its structure. Just like your amino acid, Remember, your amino acid in physiologic pH can carry negative charge sa iyang carboxyl group and a positive charge naman sa iyang amino group. And in this case, since your amino acid is carrying two opposite charges, negative and positive, it can now be called as a sweeter ion. A molecule that has a positive charge on one atom and a negative charge on another atom, but which has no net charge. No net charge. In solution and solid states, amino acids exist as sweeter ions. So please do take note, your amino acids carry what we call charges, opposite charges, positive and negative on the carboxyl group and amino group, making now amino acid as a sweeter ion. Now let's talk about the behavior of your carboxyl group when it is exposed to acidic or alkaline solution. So your carboxyl group, once exposed to alkaline solution or high pH, the normal behavior of it is to let go the proton. Again, carboxyl group will let go the proton if the group is exposed to an alkaline environment or alkaline solution or in high pH. So once it it loses the proton, your carboxyl group now will become your C double bond OO with a negative charge. So in this sense, in basic or alkaline solution, your carboxyl group is carrying a negative charge, which is kind of the same once your or when your carboxyl group is exposed to physiologic pH. Remember, when your carboxyl group is exposed to physiologic pH, it will always carry a negative charge because the normal behavior of your carboxyl group in physiologic pH is the same behavior um, it does or it possesses, right, when it is exposed to alkaline solution. The carboxyl group will always let go the proton. So same lang, same charge that the carboxyl group will carry if it is exposed to physiologic pH or basic environment, negative. Now, how about when your carboxyl group is exposed to acidic environment? If it is acidic environment, your carboxyl group, which is now carrying the negative charge, will be able to attract the protons from the solution or from the environment. Remember that the acidity of the solution is also quite directly proportional to the amount of protons that are, floating around in the solution. So if there are a lot of protons in solution, that means the solution can be very acidic. So since there are a lot of excess protons in the solution, we need to reduce the amount of protons in solution. That's the normal behavior. So in this sense, the carboxyl group sa mga amino acid that is now carrying the negative charge will be able to attract protons. So C double bond O negative plus the proton H plus na halin sa solution, we will now have the C double bond O OH. So in this sense, if your carboxyl group is in acidic solution, it will never have a charge na i-carry. Right? Butang lang, none. No charge at all. So as you can observe, if ara sa acidic or basic solution ang imong carboxyl group, may ara gid behavior ng mga carboxyl group na himuon. It will either let go of the proton or accept proton and That is basically the behavior of your buffers, right? As you can remember, your buffers work also in this way. The buffers will either accept or let go protons. So in this sense, your amino acids can also act as buffers, man. They are a natural buffer of your body. Because if there is just a slight changes in the pH, for example, gulpyada nagdubo ang pH ng blood, which means damo-damo ang hydrogen atom, damo-damo ang protons sa blood, your amino acids will be able to lessen or reduce that specific acidity or reduce that specific amount of protons sa blood by having the carboxyl group sa iyang molecular structure attached to that specific or to those specific protons sa blood. If that happens, the C-O negative sa iyong mga amino acid will now become the COO+. So, ang tanang na protons nga ara sa solution, nga ara sa blood, for example, matapik na sa kay carboxyl group. Right? So, that means your amino acids can also act as a buffer. Now, let's have the behavior of your amino group once it is exposed to acidic or alkaline solution. Now, we have, for example, we have a specific amino acid that is exposed to lower pH or acidic environment. So when we say acidic environment, again, there are a lot of protons floating around in that specific environment. For example, sa blood, no, there are a lot of protons, which means the normal response of the body is to reduce the protons because it's bad for the body, especially for the blood, to be very acidic, right? So, kailangan ma-maintain ng 7.35 to 7.45 na pH ng blood. If the blood pH drops, for example, naging below 7.35, that means the environment is now acidic for the biomolecules ng lawas. So, the normal response of the body is to counteract this one. So, one of the mechanism of the body is to have the buffers of the body act on it. And one of the natural buffers of the body would be amino acids, ma'am. They can also act as buffers, as I've mentioned a while ago. Now again, in acidic environment, we expect that there are a lot of protons in there. So the normal response of the body is to lessen the protons, right? The amino group of your amino acid will be able to react with the protons that are in the blood, forming now your NH3+. So NH2 plus the proton, we will have the NH3+. Which means in acidic environment, your amino group will carry a positive charge. Which is kind of the same with with your amino group being exposed to physiologic pH. Remember, when the amino group of your amino acid is exposed to physiologic pH, makarry man siya positive charge. Now, how about when your amino group is exposed to the alkaline or basic environment? So, basic environment, if natamaan naman ka basic ang blood, for example, the normal response of the body is to, of course, have more protons released into the blood para at least magdugo-nubo gamay ang pH ng blood so that malabot naton, mag-bring back into the normal blood pH range ang pH ng blood. So if that's the case, when we really need protons to be released into the blood, usually if we have NH3 plus na amino group sa amino acid, the NH3 plus will let go the protons para at least magdamo ang protons dira sa solution sa blood. If this happens, NH3 plus minus 1 proton, we will only have the NH2 plus sa structure ni amino acid. Right? Mabalik kita sa default na itsura ni amino group. Again, if your amino group is exposed to a basic environment, the normal response of your amino group is to let go of the proton. If amo ning itsura ka, ano ni mo amo ning itsura sa imong amino group, i-let go na si proton para at least magdama ang proton sa blood, mamat-amat no buang pH sa blood. And what will happen to the NH3 plus once you let go yung proton? It will now become your NH2. So in this sense, if your amino group is exposed to a basic environment, it will never have or it will never carry a charge. So kindly take note of this one. So in this sense, your amino acid can act as a buffer also. And that is thanks to the carboxyl group and the amino group of your amino acids. These groups, these functional groups can either, can lose protons or can accept protons. Again, the buffering capacity of your amino acids is contributed by the carboxyl group and the amino group of your amino acids. The two functional groups can either let go of the protons or accept protons depending on the type of environment the amino acid is exposed to. So at neutral pH or physiologic pH, we have a positively charged amino group and a negatively charged carboxyl group. At high pH or basic environment, your carboxyl group will have a negative pH, whereas your amino group will not have or will not carry a specific charge. Next, at low pH, your amino group can carry a positive charge, whereas your carboxyl group will not carry a charge at all. So as you can see, depends on the type of environment where your amino acid is exposed to, the charges that the carboxyl group and amino group can carry vary. Now remember, the structure of your amino acid looks like this. There's always a side chain, which is denoted by R, and there is a hydrogen atom connected to your alpha carbon. You have your amino group and you have your carboxyl group here. Now, there is an exception to this rule. Glycine is quite unique among other 19 amino acids because it does not have a side chain at all. Wala siya R part sa iyang structure. So instead of side chain, ang nag-connect sa iyang alpha carbon atom would be another hydrogen atom. So as you can see, the alpha carbon atom is being attached to two hydrogen atoms. That makes your alpha carbon atom symmetric. Symmetric because sa one part ng imong carbon atom, there is a hydrogen nga nag-attach to it. And then another part of carbon atom, may another hydrogen attached to it. So if you cut the molecule in half, you will be able to see that one part of the molecule is quite similar to the other part, or the same rather, on the other parts of the molecule, symmetric. And since there is symmetry, there is no left or right form of glycine, right? Since may asymmetric carbon atom si glycine, it is neither D or L form. It has no left or right mirror image, which means it has no levorotatory or dextrorotatory configuration. Now, proline is also quite unique among other amino acids because the nitrogen part of the amino group is also a part or attached to the ring, which is a part of the side chain of the proline. So remember, you have the side chain. Basically, the side chain of the proline becomes a part man sa amino group niya. So anyway, I will just show you how proline looks like in the succeeding slides. Right? So again, this is how proline looks like. So basically, this is the amino group of the proline. This is the carboxyl group. This is the hydrogen atom attached to the alpha carbon. And this should be the side chain. Notice that the side chain of your proline is also attached to the amino group of your proline. Basically, your proline is the only amino acid that looks this way. That the amino group and the side chains are, connected to one another. And again, the classification of amino acids is based on their side chains. The distinguishing characteristics of the amino acid would always be the side chains. We will be able to know via the side chains of the amino acids, we will be able to know if the amino acid is polar or non-polar or neutral, if the amino acid is acidic or a basic type of amino acid. So again, we will be able to distinguish one amino acid from another based on the side chain of that specific amino acid. So let's have the classification of amino acids based on side chain. First on the list would be hydrophobic amino acids. When you say hydrophobic, that means they are, again, water hating. They do not interact or react with water. So hydrophobic amino acids have side chains that contain aliphatic groups or hydrocarbon chains that can form hydrophobic interactions. So one of the examples of aliphatic groups would be your alkene, alkane, alkynes. So here are the examples of amino acids that basically have hydrophobic side chains or aliphatic groups, as well as aromatic groups also. When you say aromatic, that means they basically have rings or benzene rings in their molecular structure of their side chain. So here are amino acids that basically are considered as hydrophobic amino acids, which means they cannot really interact with water. We have leucine, isoleucine, valine, lysine, and alanine. Now, one of the subclass of your hydrophobic amino acids would be aliphatic amino acids. Remember, you have the alkane, alkenes, alkynes. The CH3, 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 right? Or the CH2 double bonded to CH, um, to CH3, CH3. Those are the examples of your aliphatic amino acids. Aliphatic group. So aliphatic amino acids basically are nonpolar and hydrophobic. Nonpolar, which means they cannot have polar interactions with polar molecules. Hydrophobic means water hating. Again, they cannot interact with water. Hydrophobicity, or being the what characteristic of being hydrophobic, increases with increasing number of carbon atoms in the hydrocarbon chain. I guess you already knew this, that as long as the hydrocarbon chain lengthens, which means gadamong carbon atom sa hydrophobic chain nga ina, gasaka man or naga-increase man ang hydrophobicity. The more hydrophobic that specific compound, the less soluble it becomes in water, and the more it becomes nonpolar.
Now, hydrophobic amino acids prefer to remain inside protein molecules, with the exception of alanine and glycine because the two of these amino acids are ambivalent. Now, if this is a protein molecule, you can expect that inside of the protein molecule, you can find hydrophobic amino acids. Whereas on the surface of the protein molecule, you can find hydrophilic amino acids. Now, I guess I've already mentioned this one, that during making of proteins, remember that the first part is for us to have amino acid chains, right? Amino acid chains that are connected together using peptide bonds. And there's what we call folding of amino acid chains. The folding of amino acid chain can be dependent on the type of amino acids that are on the chain. If we have hydrophobic amino acids, they tend to fold away from water. And if we have hydrophilic amino acids, they tend to fold towards water. I guess I've already mentioned this when we discuss about the nature of water. So during folding, a part of the amino acid chain would fold away from the water, and a part of the amino acid chain would fold towards the water. Again, it depends on the type of amino acid there is. So during the folding, most of the hydrophobic amino acids would fold away from the water. So usually they will be folded inside the protein, whereas the hydrophilic amino acids will fold towards the water. And that's why they will be found on the surface of the protein. Remember that your biomolecules, such as your proteins, are suspended on plasma, which is the watery part of your blood, right? So if this is the case, it's really fitting ang makitaan mo nga amino acids sa surface of your proteins would be polar or hydrophilic amino acids because proteins need to interact with water, right? Proteins need to interact with water. So in order for the proteins to interact with water, the proteins need to be polar or to be hydrophilic. And it will only become possible if the surface of the protein is covered with hydrophilic amino acids. Gintago ang tanan nga hydrophobic, ginpagwa ang tanan nga hydrophilic amino acids so that your proteins will be able to interact freely with water. Remember, as I've mentioned, in biochemical processes, your biomolecules, proteins, carbohydrates, nucleic acids, and lipids need to interact with water. So it will only possible for the protein to interact freely with water if the surface of the protein is covered, right, with hydrophilic amino acids. Now, there is actually an exception in this rule. Alanine and glycine are basically aliphatic amino acids, right? They are aliphatic amino acids because their side chain is basically composed of hydrocarbon. Glycine's side chain is only hydrogen, and the side chain of alanine is only a methyl group, right? So basically, the two of them, based on their side chains, the two of them can be classified as aliphatic amino acids. But they're considered as ambivalent. They're not really considered as hydrophobic molecules. They're They are not really strictly situated inside of the proteins. Why? Again, because they are ambivalent. Why they are known as ambivalent? Let's try to identify, Anay, the term ambivalent. So when we say ambivalent, that means they have um, they have the capability of interacting with water. Why? Because their side chain is really small. For example, kay alanine, ang side chain niya, ang aliphatic side chain niya ng methyl is quite, small. It only has one carbon atom, which means the hydrophobicity is basically very low. That means it does not really matter if may alanine kita sa surface ng protein because the alanine itself will not have any strong hydrophobic interaction. It will not affect at all the interaction between the protein and the water molecule. The glycine also has little effect on the interaction between water and protein because ang iyang side chain is only hydrogen atom. It has no effect whatsoever between the interaction of water and the protein. So in this sense, since the alanine and glycine since alanine and glycine are considered as ambivalent amino acids, they can either be they can be found either in the inside or outside of the protein, right? It doesn't matter. It doesn't matter where they are being placed. Glycine has such a small side chain, only a hydrogen atom, that it does not have much effect on the hydrophobic interactions. Same with alanine actually. Since one ang carbon atom, it doesn't matter at all if it can be found on the surface of the protein. So here are the examples of amino acids under the nonpolar aliphatic R groups or hydrophobic R groups. So as you can see, their side chains contain hydrocarbons or chains of carbon and hydrogen. Si methionine may paaman. It has a sulfur atom in its R chain. But anyway, going back to glycine and alanine, which are our ambivalent amino acids, as you can see, the R chain of your glycine is only a hydrogen atom, whereas the side chain of your alanine is only a methyl group. The side chains of the two of them are really small that it does not, they don't really have any effect at all to the hydrophobic interactions. So they are ambivalent. They can be found either inside or outside of the protein. Next, aromatic amino acids or amino acids that basically have benzene rings in their side chains. They are also known as nonpolar and hydrophobic. To different degrees, all aromatic amino acids absorbed ultraviolet light. So this is basically one of the characteristics of those aromatic amino acids. They have what we call ultraviolet light absorption capacity. The tyrosine, tryptophan, and phenylalanine are all aromatic amino acids, and yes, they absorb ultraviolet light. Tyrosine and tryptophan absorb more than do phenylalanine. So there is an exception on this rule. Tryptophan is basically a borderline member of nonpolar group because it can weakly interact with water molecules through hydrogen bonding with the NH ring located on tryptophan's side chain ring structure. So the rule is aromatic amino acids are non-polar, which means they don't really have that specific capacity to interact with water. But one of the members of the aromatic amino acid group, tryptophan, can basically interact with water, although the interaction is weak. But then again, the bottom line is it can still have that weak interaction with water molecules. So in that sense, tryptophan is only considered as a borderline member of the aromatic group. Tryptophan is responsible for most of the absorbance of ultraviolet light by proteins. The tyrosine is the only one of the aromatic amino acids with an ionizable side chain. When we say ionizable side chain, it can basically accept or release protons. Tyrosine is one of the three hydroxyl containing amino acids. So later we will um, show you what are the other amino acids that basically have hydroxyl group in their side chain. Right, so here are the amino acids under the aromatic R group: phenylalanine, tyrosine, and tryptophan. And as you can see in their side chain, they have what we call benzene rings.